Yeah, so this talk is about generalization of mutual information to subsystems separated in space-time. This is based on work in collaboration with Xiao Liang and Jianbin. So we know well how to characterize spatial correlations. Let's say we can consider a quantum system that is locally interacting. We can think of a quantum field theory or a quantum circuit. For the talk, I will mostly have in mind finite dimensional Hilbert spaces, but the rough picture carries over to infinite dimension. Now, say if I'm considering a subregion A, this is the spatial extent of the system, and I want to study its correlations with the region that's far away from the light cone of A, then I can consider a time slice, which, well, essentially it's a Cauchy slice, on which I can define my state. Okay, therefore, we can consider quantum information quantities that will characterize correlations in terms just of the state. Okay, there is no information about the dynamics here. It's entirely in terms of the state. And then the question will be, but what if I have instead a subregion that somehow overlaps with light cone of A? Okay, so this is where we are aiming. But first, let's consider briefly the spatial case. So with these intervals A and C. So in this case, we have a good quantum information measure that is, say, the mutual information. That's definitely a good characterization of correlations in the sense that it bounds all of them. All spatial correlations with operators supported in region A and in region B are bounded by the mutual information. Moreover, the mutual information is, in a sense, is more intrinsic than correlations of operators in that we don't have to choose any specific observables. And something we will need later, the mutual information has an operational interpretation in terms of the quantum hypothesis testing. And of course, additionally, mutual information, I don't need to mention this to the crowd, but it's useful to study various properties of matter, from static properties to dynamics, to dynamical phases, and so on. Now, let's go back to our question. What about time-like separated regions, such as these A and B? Of course, we cannot, the standard mutual information does not carry over in this case. That's because B depends causally on A, so they belong to two different Hilbert spaces. Nevertheless, we know this is a well-defined question. It's a physical question because this is related to dynamical correlations, unequal time correlation functions, which may be useful to study, dynamical properties of system, transport, causal structure, things like that we like to think about, thermalization, quantum chaos, or lack thereof, and so on. So then the goal here will be to try to address this question, which is what's a good quantum information measure that captures all space-time correlations between two subregions of the form of A and B, which can be causally correlated. So more precisely, we look for a quantity that, first of all, bounds all natural, meaning Schwinger-Keldysh ordered time orderings of unequal time correlation functions, just like the mutual information in the spatial case. And then it reduces to the mutual information when we consider spatially separated regions. And also it has a quantum hypothesis testing interpretation. It has an operational meaning in terms of a quantum hypothesis testing. So here is the outline. So I will start by briefly reviewing the spatial case, basically collecting the properties that we need on the way for the rest of the talk. Then I will propose our spacetime generalization, and then I will discuss connections with quantum channel discrimination. It's not QCD. It's not quantum covariance. And then in the last part, I will discuss a couple of simple examples in the context of many-body dynamics. Good. So let's start by briefly reviewing the spatial case. So first of all, the mutual information, I guess everybody here knows the definition, but just for the record, it's a combination of von Neumann entropies for the joint system A and B, and the reduced state on the system, on the subsystem A and the subsystem B. As we mentioned previously, this is a measure, this is a characterization of correlation functions in that one can show this upper bound on suitably normalized correlation functions for any operators supported on region A and region B. This can be easily proved using the p-scale inequality. And then another property, actually even more crucial that we will need, is that the mutual information is a relative entropy. Okay, so we can actually write it as the relative entropy between the joint state for the subsystem AB and the factorized state, rho A and rho B. Conceptually speaking, we can view the relative entropy as a symmetric measure of how different two states are. Okay. And this leads us to, to the next part, which would be basically constructing the relative entropy in terms of the quantum hypothesis testing. So this would be our key concept, key starting point. And we will then try to generalize this to space-time. So let's briefly go over what we mean here by quantum hypothesis testing. So suppose we handle a system in a state. Okay? The state can be either rho or sigma. We don't know which one of the two states, but we know it's either rho or sigma. Okay. And then we need to come up with a good strategy to try to decide with as high probability as possible what's the true state of the system, whether it's rho or whether it's sigma. So a natural strategy would be to consider several copies of the system, and then on each of them apply a measurement. Say, like I want to measure the spin or some other quantity, and then I repeat this measurement several times. I collect the frequency of the outcomes. Say again, the values of the spin and so on. And then from the frequency of the outcome, I extract the probability associated to my measurement, to my observable. And from the probability, I will decide whether the state is rho or sigma. Okay, if probabilities go roughly like QI, it means it's sigma, otherwise it's rho. And this is, of course, a probabilistic approach. Okay, in general, except for special situations, we are not sure, we cannot reach uncertainty with a finite number of copies. But nevertheless, we can asymptotically make the probability of being wrong as small as possible. In particular, if we repeat this measurement a large number of times, capital N, then the probability of confusing the two states, more precisely, the probability of mistakenly think that the state is sigma, but in reality is rho, goes like the exponential of -n times the classical relative entropy between these two probability distributions. Okay. So this is just a Stirling approximation with some combinatoric reasoning. That's how we obtain it. So one can do better. It turns out that one can actually consider simultaneously n replicas of the system, and then perform a collective measurement that sort of cross-couples all the replicas, can cross-couple all the replicas. And for a suitable choice of this measurement, it's a one-shot thing, but it's a big, yes?
Paolo, I just received an email from people in the audience that I think they're asking you to share your screen, because I think they can't really see.
Oh, I see. Yeah. Oh, thanks for the heads up.
Thanks, Xiaoliang.
Okay. Thanks, Xiaoliang. Okay. See, there is. Good. Okay, hopefully now. Good. Great. So, so good. So we can come up with a better strategy in which we consider, I was saying, simultaneously all copies of the system. We perform a one-shot measurement on this, a suitable measurement, which turns out, for a suitable choice of this collective measurement, we can improve the probability of guessing the wrong state. Sorry, we can, I guess, lessen the probability of being wrong. And in particular, the probability now for large n will asymptote at the exponential of a different quantity, general different quantity, which is the quantum relative entropy. So the quantum relative entropy, it's just the definition that we all know about of the quantum relative entropy. This can be shown to be larger, greater or equal to the classical relative entropy. Okay. It's also just implied by this reasoning, because this strategy of measuring, this strategy is a special case of this strategy, right? So this better be true. And indeed, the inequality holds strictly. The equality holds if and only if we are basically in a classical situation, so the states commute. Good. So we can, as rho and sigma, we can consider the connected and the disconnected state, just like we wrote here, and that will be, that will give us a operational meaning for to introduce the mutual information. So we're going to use this type of reasoning now to introduce a space-time generalization. So I will now slowly introduce some notation in presenting our proposal. So let's start by considering a quantum system, which is in an initial state rho in. So here, this triangle will always denote the initial state. Now, we split the Hilbert space into A and the complementary A bar. There is an evolution here. We don't need any, we are not assuming anything. It can be non-local, it can be the most general. It doesn't even need to be a unitary, it can be a quantum channel in principle. Anyway, we have an evolution, and then after the evolution has been applied, at the later time, we split our system with a different partition, which we call B, and then the complement B bar. So this symbol here simply denotes that I'm throwing away information from this part of the system. This is just, I'm tracing over my complement of B. And here I'm keeping this connection open. That just means that I'm not yet contracting tensors. I'm not yet contracting operators. So again, this region A is like this guy here in our previous diagram. And region B is in the future and may be overlapping with the light cone of A. Okay. So we are interested in defining some kind of mutual information between these two regions. Now, again, because of a possible causal connection, then A and B belong to two different Hilbert spaces. So somehow we want to, perform measurements in some sensible way here, so that we can still extract information about unequal time correlations, about dynamical correlations. Good. So here is our general strategy. Here is our basic idea. Now, the key here is that we need this is a necessary point, we need to consider an auxiliary system, W, which we call ancilla, and to couple it in a suitable way with the subsystem in the past. The reason why we need to do that is because, again, I want to somehow compare the information here with the information here. But in order to do that, I need to have them in the same Hilbert space. So roughly speaking, I want to sort of move these degrees of freedom to the future, okay? To the future, so that then I have them at the same time as B, and then I can compare them. So schematically speaking, the natural strategy is indeed to somehow use an auxiliary system which acts as a proxy for the information contained here in the future, and bring it in the future. Okay. Now, so this V, this is a unitary. We assume it to be a unitary. We can always take it to be unitary as far as we make the ancilla sufficiently large. Okay. The ancilla, we can just consider it to be initiated in some reference state. Doesn't matter what it is at this stage. And then we want to somehow optimize, we want to choose an optimal and adaptive coupling between system and ancilla, so that as much information as possible is carried over to the future. Okay. Now, what does it mean? How do we quantify the amount of information that we bring to the future? How do we quantify what's the best strategy, the best unitary, the best V? Good. So now we take another inspiration from the spatial case, from the mutual information case. Remember that the mutual information is the relative entropy, is roughly the difference, so to say, between the connected and the disconnected state. So here we want to somehow disconnect region A and region B. And here is our disconnected version of the state. So what I'm doing is I take a trace over this copy of B, and then I substitute it with the unperturbed evolution. Okay. Forget for a moment about this tensor product. Here I just have my initial state, the unperturbed evolution, and then the final system B. So in this way, the correlate, if I consider an operator insertion here and here, this would be uncorrelated, obviously. It's just factorized. Good. Now, the last ingredient in the strategy, again inspired by the quantum hypothesis testing, is that it could be in principle that if we consider multiple copies of the system, just like before, so we have multiple copies of the initial state, which just we act on it with a factorized tensor copy of the unitary, of the original unitary. And then we consider a coupling to the ancilla that can collectively couple to all the replicas. Okay. It could be that this method, like considering multiple replicas, will lead to even more information to the future. Will allow us to sort of to move more, to bring, to push forward even more information to the future. And we will see later whether this is true or not. Okay. It's actually a rather non-trivial question. So good. So said all the ingredients, putting them all together, the final expression for our proposed spacetime generalization is that we consider the relative entropy between the connected and disconnected states. We could say they are spacetime states. Okay. Again, in the sense that they collect information about two different times. We consider the relative entropy, and then we optimize this relative entropy over the strategy of how we couple to the ancilla. So this is precisely the quantity that we want to optimize, our functional. And then, so this prefactor of 1 over n is because this quantity here, say if I consider multiple copies, this quantity here will at least be additive. It may be super additive, but at least it will be additive. So it's just natural to just normalize it by the factor of the replicas. And then again, from the reasoning from the quantum hypothesis testing.
Canada in recent week shock and made people all over the world.
Okay. That's a good comment. So again, from the quantum hypothesis testing, we know that the probability, in particular, the probability of being able to, of confusing these two states goes asymptotically like the exponential of minus this spacetime mutual information. Okay, so this is the main character of the story. Are there questions so far?
You said it could be super additive?
It could be super additive.
Do you know that?
Oh, sorry.
In the range the n goes infinity, maybe.
Yes, so it could be, yeah. It could be that even if I consider a finite, like two copies, it could be that the sum is greater than twice the single copy.
Yeah, but I'm just saying if it then goes to large and larger,
Yeah.
Is it possible to be proportional to the higher power than 1?
Or to higher power than 1.
Otherwise it's really fine.
I don't have a good answer to that, but my spontaneous, I don't think it would be the case. Like, okay, there are counterexamples for quantities like this where we know there are super additive examples and
Finite n.
yes, and at finite n, right? One can easily, generalize it to higher n, and I don't think the powers there would be bigger than 1, but I don't have a way to rule it out.
Could you tell how is the reply, how big is the reply when the A and B spacetime separated?
Oh, great. I will say it probably in the next slide. Good. So, so now in the upcoming slides, I will indeed mention a couple of basic properties of this space-time relative entropy. And then we will see a few examples and connections to quantum channel discrimination and other things. Okay, so the first property indeed is, of course, we want this quantity to reduce to the standard mutual information when A and B are spatially separated, and that's indeed what happens here. So yeah, we can say consider some local circuit. Here, if you stare at these gates, you'll see that B is causally disconnected from A. In particular, that means that it doesn't B doesn't feel how I couple subsystem A to the ancilla. Okay. And from this basic notion, one can easily show that, first of all, it's sufficient to consider an ancilla that is isomorphic to A, and to choose the coupling to be the swap operator, so that I can bring outside, I can simply just bring outside my subsystem A, but then at this point, overall we have a state with this B region and A region. They are disconnected causally. So this is just a standard spatial state, so to say. This is just a state, okay? And therefore, the best we can do to discriminate connected and disconnected, we know it's given by the standard mutual information. Okay. So with some simple algebra, one can indeed show that that is the case. But then, if instead A and B are causally connected, we cannot just choose V to be the swap. Okay, the optimization becomes much more non-trivial. In particular, a simple difference that we can already appreciate in the time-like separated case is that this space-time relative entropy can be split into two parts, two contributions. One is truly a mutual information, in the sense that, in particular, it satisfies the usual bound on mutual information, given in terms of the Hilbert space dimensions of B and W. And more precisely, this writing means that I'm considering, remember, this is the connected state. I'm going to present this picture many, many times in almost all the slides. This is our connected state, okay? We're going to, again, talk about connected and disconnected state. It's always these two guys. Now, let's go back to the connected state. This is the mutual information between the ancilla and the system in the future, and the subregion in the future. And again, this has all the properties of a standard mutual information by construction. Whereas the second term, the second term is there only if we have causal relation between A and B. This is a genuine relative entropy. In particular, it can be divergent. Okay, it's unbounded, because the relative entropy can be divergent. And again, it basically accounts for the difference between the perturbed and the affected and unaffected state by the measurement. What does that mean? Consider again our connected state. Let's trace over the ancilla, so we are left with this. This is a state defined only on B. And we can view it as the evolution with our evolution operator perturbed, affected by the presence of the measurement in the past. Okay. So the relative entropy between this perturbed state and the unperturbed state will be there as far as subregion A and B are causally related. Okay. So this will be non-zero in general. And again, this is another way to see how our quantity reduces to mutual information in the spatial case. In the spatial case, B doesn't care what we do here, so this term will just vanish. Okay. And then this again simplifies to the standard spatial mutual information. Okay, so another important property which we promised to try to reach in the introduction is that this quantity actually bounds any time ordering of correlation functions between region A and region B with any arbitrary initial state. So I guess I'm not going to go through the proof. But I can just mention that the key idea of the proof is, remember, this is our connected state with a suitable ancilla and with some suitable unitary connected ancilla with the subsystem A. So the key of the proof is to consider a suitable coupling, ancilla and system. And the role of this specific coupling is to introduce operator insertions. It's basically a control gate. Okay, and depending on the state of the ancilla, I insert this or that operator, and it's chosen in a suitable way so that overall it's chosen so that I can rewrite my 2-point functions as expectation values of my future time operator using this suitably chosen ancilla plus system state. Okay. So this is the key of on how to relate correlation functions to this particular to this spacetime relative mutual information. In other words, the key is that I have an ancilla which couples in the best possible way to the past subsystem, and therefore it should in particular be able to capture any correlation, any information in the past, and therefore any correlation function between A and B. Okay, so we simply have to choose a specific coupling. Okay, it's not a trivial thing to choose the suitable coupling, but turns out it's possible. Another comment that one can make is about this prefactor. This prefactor is important to tell us that this proof is optimal. It's optimal in the sense that, so it turns out that this 1/8 in the spatial case reduces to 1/2. Why? It reduces to 1/2 because, so if these two operators are spatially separated, this is just twice the symmetrized product. But now these operators can commute, okay, because it's spatially separated. And then I take a 1/4 from here, and this just gives me the standard spatial correlation function between A and B. And I'm left with an overall 1/2 here. But 1/2 is precisely the prefactor in the spatial case. Okay. So this means that we really reached an optimal spacetime generalization for these bound on correlation functions. Oh, it's a convention because this is an anti-commute. This is the response 2-point function. This is the retarded 2-point function, and it's a convention to put a factor of I because we have a commutator.
In the spatial case, there's also, I guess you suppressed it, but also like a subtraction of the.
Oh, yes. I forgot to put the connected. Yes.
Yeah, so
is that what you? Yeah. Typo.
There's an analog term in the new terms.
Yes. Yes, here I put it. So we subtract the disconnected. And actually, the disconnected component precisely comes from this guy. Because it's just the product of this operator insertion and this operator insertion. They don't talk to each other. So, yeah.
Question?
Yes.
So this reduction to the Cauchy slice, well, you know this prefactor 1/8, it's tied for anti-commutator because you can relate it to the previous case, but what about the commutator case? Is it also tied?
Yes, that one I cannot relate. Like, this is an inherently dynamical quantity, so I don't know how to relate it in a simple way to. Of course, you can do analytic continuations and stuff. That's a good right. But here we are dealing with fully generic initial states, so let's not mediate whether there is a simple connection with the spatial case. Yes, at least to me. 10 minutes. I'll have to speed up. Great. Good. So now let's go to the next part, which is interesting connection with the subject in quantum information, which is quantum channel discrimination. So this is the exact analog of the quantum hypothesis testing for channels. So we don't care about states. we care about evolutions. We only care about evolutions. And the idea is that, I should have probably mentioned more explicitly, but the idea is, let's say we're given, two quantum channels, just two generic evolutions consistent with unitarity, positivity, complete positivity. Trace preserving, consistent with positivity and with complete positivity. And we want to come up with a strategy, with a probabilistic strategy to measure the difference, to sort of estimate the difference between these two channels. Okay. An example could be the so-called quantum illumination, where, say, I have a distant object. I want to shine it with some photons. And then, depending on the signal that I get back, I can decide whether the object was there or not. So this is really channel discrimination, because whether the object was there or not determines the evolution of the state of the photon. Okay. So the idea is to come up with the best state, for the initial state for the photon, so that I can maximize the probability of seeing the object. And it turns out that, somehow coupling say, if I start with a single photo.
Sorry, are you maximizing the probability of seeing the object or discriminating between the object?
Good. It's the same as the quantum. Well, there are different versions, actually. But one version is the entire analog of the quantum hypothesis testing, the way I mentioned it before. The probability of confusing the two states. Yes. That's this guy, yes. The probability that we think the state is sigma, the second one is the null hypothesis, but in reality is...
If you're picking a particular hypothesis, like the object is there, and then you're computing only the probability of falsely concluding that it's not there.
Sorry, can you say again?
Are you picking a particular hypothesis and you're only worried about getting that one wrong?
So, well, I know that it's either that or the alternative one. I only have two.
Yeah.
I don't know if that answers.
I guess I'm confused about. So if you say the probability of seeing the object, you could just choose some protocol where you always see it, and it's just wrong some of the time.
Right. So I guess the point here is that, for example, in this quantum illumination, one of the channels is the signal that I know what I will get because I know what object is there, and the other hypothesis is just background noise. So I have two channels, and I have perfect knowledge of the two channels. I just don't know which one will actually be that I get. Yeah. At least that's the basic setup. Good. So okay, this was actually the tour. Anyway, maybe I can be a bit faster here. One can show that in a special case, in which, so remember we are considering, this is the general situation. We have a bipartite initial system with some state. The state can entangle both subregion A and the complement. Now, I'm going to assume a special form of the initial state. I'm going to assume, first of all, that the initial state is factorized between A and the complement. And so we write this way. And the second assumption is the initial state of A is pure. Okay. So if we are in this special circumstance, then our spacetime mutual information reduces to our optimization problem reduces to this quantum channel discrimination, because that's what people do in that context. In particular, if I want to shine my obstacle, I throw at it a pure state. Yeah, and there is no complementary. This is the photon, and this is the ancilla of the photon. Okay. So basically, one can rewrite our optimization in a slightly simpler way. Which, luckily for us, a few years ago, the exact same quantity was proven to actually be additive. So this goes back to one of our original questions. So in the special case in which I have this factorization and this is pure, then indeed this quantity is additive. And it can be basically proven by what some people call the chain rule for relative entropy. Now, it's just some inequality in terms of, so basically one can majorate this relative entropy of the output state in terms of what we call J1. It's just a single copy relative entropy extremized over all possible initial states. It's called, sometimes it's called channel relative entropy. For people who know it, it's also related to the diamond norm. This is the relative entropy version of the diamond norm. So basically, by induction, one can show indeed that this quantity, in this special case, is additive. I should also mention this chain rule is nice, but it's very delicate. One can easily find counterexamples, such as in this paper here. And we were lucky in particular because our situation boils down to comparing the channel n, which is just our original evolution here. When I trace out the complementary system, the evolution reduces to some channel n. We want to compare it with a replacer channel. Okay. The replacer channel is a channel that takes any input and just spits out the same output for any input state. And only in this case, this chain rule was proven, okay, a few years back. So we were quite lucky that indeed, at least in this special case, we can apply it. And of course, it would be very interesting to understand if these, in our setup, we always have some kind of replacer channel because of the disconnected state. But our situation generalizes the quantum channel discrimination story quite a bit in that we don't deal with quantum channels. In particular, if the initial state is not factorized, if we have entanglement between A and A bar, the complementary, tracing out the complementary system will lead to an evolution that is not a quantum channel. So this is a sharp generalization from the quantum channel discrimination case. So it will be very interesting to explore whether we can apply similar type of theorems in that context. Okay, maybe.
2 minutes.
Oh, okay, perfect. Okay, now let me go through a couple of simple examples. Actually, the simplest thing that we can think of is we don't really have evolution. The evolution is just the identity operator. But the nice thing here is that everything can be done analytically. So at least we can get some intuition on very, very basic building blocks. But I guess I won't use these 2 minutes for going over the analytical derivation. The final result, let me just say, is here. So basically, we're interested in discriminating the connected state from the disconnected state with a trivial time evolution. So certainly there are non-zero correlations, like the system has perfect memory. So correlations are as large as it gets. And indeed, one can make this space-time mutual information arbitrarily large. Say if my initial state is almost pure, then this thing will diverge. The second example, so we simulated a system in a full many-body localizing phase. So in this phase, the dynamics is, well, these are by now very well studied. This is a very well studied phase. The system is known to possess a complete set of commuting localized conserved operators. In particular, they are localized. Okay? That means that our system has memory of local details of the initial state. Okay? So that means, because of this local memory, it means that even if I take subsystem A and B to be very small, such as 1 qubit each, then because of this strong memory of my MBL evolution, one could expect, say, inspired by this very simple situation with trivial evolution, one can expect that our space-time mutual information will be very large, okay, in this MBL context. So we simulated a particular, we simulated a couple of models, but this one is it's a quite canonical model in the MBL context, random field Heisenberg Hamiltonian. So this is the behavior we find. There are a few comments. So the early time behavior is dominated by, it's basically log t, diverges. If I start from a pure state, Okay, these are some details, but anyway, it doesn't matter. If I start from some pure state, from a pure state in the qubit I'm probing, then initially I have a logarithmic log t behavior, and that's a rather straightforward reasoning to conclude it. I guess I will probably skip the reasoning. Another comment is that as I increase the localization, the local memory of my evolution, of course, gets stronger and stronger. And indeed, one can observe that these asymptotic values increase arbitrarily, at least in this model and in the other models we simulated. And another property worth mentioning is that depending on the initial state, the asymptotic value will be different. Okay. So here, really, we can exploit the fact that our quantity encodes the initial state of the subsystem that we are probing. In particular, the closer the initial state is to be an eigenvalue, a localized eigenstate, okay? Sorry, an eigenstate of a localized conserved quantity. The closer the initial state is to that, the more the state will be preserved, and therefore the higher the asymptotic value of the mutual information, of the spacetime mutual information will be. And then as a comparison, we looked into a very efficiently thermalizing system. This system is very thermalizing in that it doesn't even conserve energy. It's a Floquet system with a suitable choice of parameters. And indeed, we see that, the expectation is that the memory is very short. And indeed, what we see is that this spacetime mutual information decreases very, very quickly. Independently, these are different initial states, and roughly the behavior is the same, as opposed to the MBL case. And with this, I will conclude. So we proposed the spacetime generalization for mutual information. There are various properties that this satisfies. And then here for the future directions, as we mentioned, one open question is about the additivity, especially when we are dealing not with a quantum channel. This is a sharp generalization. This would be a sharp generalization from the quantum channel discrimination. It would also, so this quantity involves taking a supremum over a unitary. That's not an easy job usually. So it would be very interesting to find, say, a simpler quantity that maybe it's not as large as this mutual information, yet it can bound all the spacetime correlation functions in the way that we saw in the theorem earlier, but without implicitly taking a supremum over couplings to the ancilla. This is not clear whether it's possible. And then relations to other quantities, as well as applications to other systems beyond MBL and fully thermalizing. Thanks.
So sorry, just to clarify, you said that the relative entropy chain rule doesn't hold for a certain class of channels. Because my understanding in the paper, or correct me if I'm wrong, the chain rule should always hold, but additivity doesn't necessarily always hold for general channels. But the chain rule should still be true, right? Because the chain rule is just a statement about like the relative entropy.
Well, I think you can use the. Sorry, no, the chain rule definitely. This is very non-trivial. This is a very non-trivial property
I
too.
mean the second paper down there, and they prove like a general chain rule in terms of like this like.
It's a different chain. It's not this chain.
Yeah, it's a different chain rule.
Yeah, it's weaker.
Yeah, and okay, so that weaker chain rule should still hold, right, in this case, right?
Yep.
And
Oh, sorry. I don't know if it holds in our case.
okay.
Yeah.
Because and this is related to your point about maybe finding some way to get rid of the supreme. Like, one result of this chain rule they prove, right, is they prove that adaptive strategies aren't better than parallel strategies.
Mm-hmm.
So
Asymptotically, yes.
yeah, asymptotically, maybe you can replace somehow. You can try to use it like a parallel strategy or something to get rid of the supreme.
Yeah. So right. So this stronger chain rule can be, if you find a counterexample to additivity, then you can reverse it and use it as a
So in EDCFTs, you
Yeah, that's a very good question. Right, so it's, okay, the short answer is it's not related to this quantity, despite this reduces to mutual information when you have spatially separated regions. So which sounds kind of strange. Like, then you say, but then if you do analytic continuation, you would recover this, right, when you go to when you pass the light cone. But, so the caveat is that if you have correlations, if you have a spatial time-like correlated regions, this quantity actually diverges on a CFT anywhere inside the light cone. So it would be very interesting to understand if one can sort of subtract off divergences to make sense of this. For example, by restricting the unitary, the couples and silent system. For example, in a way that, so you want to restrict this guy so that there is a finite energy that is transferred. Actually, there is literature on that in this quantum channel discrimination context. Of course, not from perspective of CFT, but that might be an interesting starting point. Yeah, what you said, of course, it's a well-defined, this analytic continuation is a well-defined thing to do. But unfortunately, so we tried to play around with the quantity, but it doesn't seem to lead to very good quantum information properties, such as this. Yeah, I don't know how to prove these bounds on correlations, for instance. It doesn't seem to be able to prove it. Yeah. Thanks.